Steve,
There and everybody else is.
Steve doesn't bring them?
He hasn't been there like the last two.
Oh. Okay. Well, all right. No. Oh,
I see you've been practicing.
no, this is what it was. All right. This was working again. So we're going to talk about inductors and all this good stuff about them, permeability and core material, and then do piezoelectric devices. No, I don't know. Okay, so all a solenoid inductor is a coil of wire around a cylindrical core. Could be air or and a lot of times what you saw in older AM radios in particular was a ferrite rod with the coil wrapped around it. It also served as a internal antenna. A toroid is essentially the same thing, except that core is wrapped into a toroid like a donut. So when you wind the coil around it, it concentrates the magnetic field within the toroid, whereas in a solenoid, the magnetic field extends outside of it. So it affects adjacent things. With the toroid, 90-something% of the magnetic flux lines are contained within the core of the toroid. So you can have them relatively close together without having interference, which is one of the things you see on any of the modern radios and stuff. Things are packed as close as they can get them. The other real difference is for the same amount of inductance, it turns out to be a physically smaller package. The inductance is really based on the permeability. So if they have the same core, the permeability will be the same. And then it's the length, the number of turns, and the cross-sectional area. So that gets sort of optimized when it's a toroid. And there's a nice picture of a toroid. Kind of showing the magnetic lines contained in the center. If Rick is interested, the inductance formula is over there, although
right
there aren't any questions where you have to find the inductance.
Why you know?
Because I know all the questions.
Okay. Okay.
I've read them once or twice. So
go back again for a second. What are the units of measure on some of those? Just for curiosity. So we got
I think H is Orsted's.
what is H?
Orsted's, which is the magnetic flux. I think that's what the H formula is.
So that
and mu, wherever mu is permeability. Okay. N is the number of turns, so it's turns squared.
What's A?
A.
A for apple.
Oh, cross-sectional area.
Oh, yeah. Okay.
So
measure,
and it's kind of counterintuitive, but the larger the diameter of the coil, it increases the inductance. But you're also dividing it by 2 pi times the radius.
Right.
So it's one of those trade-off sort of things. And all 2 pi comes up again. I should have talked more about that on the resonance stuff on why everything is related to 2 pi. Took me a long time to figure that out.
Radians.
Radians.
Don't need to know that, but
Huh?
don't need to know that for the test. But
No. In fact, I don't think they ever talk about radians, which
Yeah,
is
yeah.
in college, that's all we did was radians.
Inductance 2 pi FL, capacitive reactance 1 over 2 pi FC, 2 pi shows up everywhere.
Right. Or simpler is omega L or 1 over omega C. So that's shorter. Okay, you ready?
Maybe.
So what's the primary advantage of using a toroid versus a solenoid?
It's the magnetic. The cold.
A. Okay. A. What core material property determines the inductance?
T.
And we usually use the mu sign to represent permeability. There's essentially 2 kinds of cores. Well, actually 3, but in this part, we're only talking about powdered iron versus ferrite. Powdered iron doesn't have the same permeability. In other words, you can't get as much inductance, but it'll operate at much higher currents.
Is that because it's less likely to go up?
I don't know if it's the heat or exactly what, but that's definitely the problem with ferrite. As you put more energy into it, it heats up, and the heat causes the permeability to go down and starts to saturate, and then it no longer.
Powdered is compromising, getting the or benefit without.
Yeah,
Because
I don't know all the physics.
I imagine at some point you'd have to increase the core bigger and bigger and bigger
Right.
to absorb the energy.
And that's what you do for if you want more power, you stack 2 or 3 toroids and wind them.
It's not even reasonable, and so maybe that's why they went to the power.
And also, you can generate enough heat on the ferrite to actually, you put 1,500 watts in, they can blow up or at least crack. Plus, and I don't know what the mechanism, but if you heat them enough, it permanently changes the permeability. Ferrite beads is another example. It's kind of a toroid, and you can get them at what they call clip-ons or snap-ons, where it's split so that you can put it around an existing cable that has a big connector on it that you can always slide a bead on. But you can also buy them as solid beads. They make very good chokes if you build it and put them on, about 5 or 6 of them on a piece of coax. They also use them on power amplifiers in transceivers. See them internally to get rid of spurs and harmonics. That's what the clip-ons look like, and come in all different sizes, and you can put multiple turns through one also. So why would you use a powdered iron core rather than a ferrite?
Higher current.
Everybody go with Bravo? So what's another reason to use ferrite cores rather than powdered iron?
Fewer turns.
Is that true? Yes. Has higher permeability for the same volume. Okay, what do you use in VHF, UHF as parasitic suppressors?
See? So they're not as effective for HF?
It depends on the material, the mix. And if you look,
You said put a bunch of them in.
yeah,
So maybe
yeah, the more you do,
maybe that's what you need for HF. You just put a bunch of.
well, each one gives you a certain amount of inductance. So you put 5 of them on, you get 5 times the inductance in theory. And it works out almost that way.
Come a lot on USB cables.
Oh, yeah. And those kind cost more, but if you don't want to do your own, you can buy them already installed on USB and audio, some audio cables you can find with them.
No, they're cheap now. I bought a case of them from
Yeah,
10 of them from Amazon for like $8 or something like that.
yeah, I got a whole assortment. I think there's more than that in here.
Yeah, I mean, there's a bunch, yeah.
Yeah. Okay. So one of the things you got to watch out for, and we talked about, is you got to design circuits so that you're not going to saturate the core. When you do that, it stops creating additional magnetic flux. As you run current through the coil, okay, the more current, the more the magnetic field builds up, more energy you store. At a certain point, when you start to saturate, it's like the permeability just starts decreasing. So you no longer are increasing the magnetic field, which means since it's not changing or changing as much, the field that you see on the output of a transformer decreases. So it no longer acts like a transformer at that point, and you'll see a steep drop in the output waveform.
Is that saturation value variable or is it?
It depends on the core itself, the material, the size of it, how much power you're putting in. And I think it relates back to that formula for the H, the Orsted's. That's the value of the magnetic field.
The inductance formula?
No, the one on the other side that wasn't highlighted,
Oh,
the
okay.
H.
Yep.
And if you do saturate it, and the temperature gets high enough, which is another factor when you're doing that, it can change the inductance permanently. This is one I found showing the normal output from a transformer. And as you start to saturate the core, what happens, and you see this very sharp drop because the magnetic field is no longer changing. And that's what causes the output on a transformer, is the magnetic field collapsing or increasing.
If you've ever wound your own current, what do you call it? Current transformer,
Yeah.
common current
Okay.
transformer, right? And I did one on a small core, and I wound it like with 20 gauge wire.
Okay.
And then I tried putting it on my transmitter,
Yeah.
and it worked great for about 4 seconds. And then SWR was like 1.2 to 1. And then you watch your SWR go, whoop, and that's what's happening.
Yeah. Wasn't the wire would have been big enough. So
Little core.
you just put too much energy into the core. If you do it again, use 2 cores. It'll last twice as long.
I'm still holding on to change the antenna.
SWR
Huh?
and have good SWR.
Yeah. So what is inductor saturation? Right. Okay. Now, another problem you have with inductors is self-resonance, because like most things in the world, everything has some stray capacitance. So when you wind a coil, the spacing between them acts like a dielectric, and it's like two plates. So you have an electric field and it becomes a capacitor. So you have a typical circuit.
Someone trying to join.
Whoops. How do I do that? Oh, it's not going to let me.
Is someone trying to join?
No, Jesse, just Jesse. So the effective circuit for the inductor is you've got some series resistance and you got that inter winding capacitance they call straight capacitance. So the closer the coils are together, the more capacitance you're going to have. And you spread them apart, you decrease the capacitance, but you're also decreasing the inductance. So it's kind of a game that you play to put the self-resonant frequency someplace where it's not a problem. And of course, we also remember from last week the self-resonant frequency. Remember that one?
I think I had to leave early.
Oh,
Mm.
remember how you set inductive reactance equal to capacitive reactance? It's all for F.
Let's do
And you get
three.
1 over 2 pi times the square root of LC. So if you can figure out what the distributed capacitance is, then you can calculate what the resonant frequency is going to be, the self-resonant frequency.
Well, how do they do that when you're working at 3 gigahertz or something like that?
The same way you do it at 1 kilohertz.
Well, if you look at it different, it's going to change. I mean,
Well,
you know,
it's like Heisenberg.
exactly. Yeah.
So what's the primary cause of inductor self-resonance?
Capacitance.
Interturn capacitance. Okay, you can have a variable inductor. One of the ways is to have and they used, I guess they still do it. They used to make them where the coil form was actually plastic with threads, and you had a slug made out of either a iron powder or ferrite or brass, and as you rotated it, it would go in or out, and you could actually change the inductance of the coil.
Well, the early tuners.
Yeah, IF strips, the transformers were that way. They were tunable with a little, it was probably powdered iron back then, but one
The
of the
first tuner I ever built was on a cylinder, one with wire, and then some a gizmo to track it. As you turned it, the whole thing gizmo would move up and down the coil. You know.
the basic difference, if the slug is made out of ferrite or iron powder, it's going to increase the inductance as it is moved inside the coil. If it's brass, it actually decreases the inductance because its permeability is less than air. So what material is commonly used out of the list?
Polystyrene would get you too far.
Actually, I still have a bunch of them where the core is polystyrene.
Really?
Yeah, that's why you used to get coil. In fact, you used to be able to buy them with 4 pins on it that would plug into a tube socket. And that's how you change coils on one of the really old radios. And you just plug a different one in, like plugging different crystals in. Which type of material decreases inductance? Okay, a transformer is 2 inductors that are closely coupled, meaning they share the same core. And it's called mutual inductance because the magnetic field from one winding is affecting the other winding. So as the magnetic field increases on, let's say, the primary, it's going to induce a current and an opposing magnetic field on the secondary. The turns ratio is going to tell you the voltage increase or decrease across the transformer. In other words, they have the same number of turns on the primary and secondary. It's like a 1-to-1. If you put 12 volts in AC, you get 12 volts out, minus some core loss, but they don't talk about that. If it's got a 10 turns in and 100 turns out, your secondary would be 10 times the voltage on the primary. Since the power in equals the power out, okay, if you increase the voltage on the primary or secondary, you're going to decrease the current because you can't have a power gain. It's a passive device. So the main thing is knowing what mutual inductance is and the turns ratio and how it affects current and voltage. There's another effect called the magnetizing current. So if you put current into a transformer and there's nothing connected to the secondary, you're going to get some magnetizing current flow. It's like the minimum required. It's like a threshold amount of magnetic field that's required. And you see this kind of a waveform where you see the magnetic flux increasing along with the input waveform, except you notice it's 90 degrees out of phase because it's related to the current. So the voltage in this case is leading the current. And that's, if you remember Eli. You don't remember Eli? Eli the Iceman?
In an inductive.
E, voltage, and an inductor, L, leads I, the current.
Okay,
Did you leave before that?
I think I did.
Okay, that's good, because I would hate that you didn't remember it.
Well, you know,
All right.
More provision.
Huh?
More provision.
Yeah, there you go. A lot of times transformers are used to match the output impedance of one circuit to the input impedance of another, like your transmitter to your antenna. And in a lot of cases, you'll do that match with a transformer as opposed to a LC circuit, which we'll talk about later. So again, you need to make sure that you're not saturating the core because of all the bad effects. It even creates harmonics, third harmonics. And according to my research, that's when you start saturation, that's what happens is the output becomes 3/4 of the primary signal and minus 1/4 of the third harmonic of it. And when you add those together, you get a waveform kind of like that. So what is current in the primary winding of a transformer called if no load is attached to the secondary?
magnet, yeah.
Why should core saturation of an impedance matching transformer be avoided?
Okay.
I don't know. Maybe it's male. All right. piezoelectric crystals. Uh, they've been around since kind of the beginning, and they're still used today. It's a piece of quartz that's machined a certain way, with I don't know if they actually plate them or just put metal plates on it to hold it. And it has the effect of physically changing the crystal size when you apply electric field to it. And kind of like an inductor with the straight capacitance, it has a self-resonant frequency. So if you apply an AC voltage at that frequency, it'll act just like a tuned LC circuit and it'll resonate. So if you put in enough energy, just like the tuned circuit, to overcome the loss, because there's some internal resistance from it vibrating, it becomes a resonant circuit, and it's very narrow band, which is why it's used as reference oscillators and in crystal filters, because of the narrow bandwidth. You can put a bunch of them together and call it a crystal lattice and get a very nice shaped passband. The equivalent circuit is what they call motional capacitance, because as it physically moves, changes shape, the capacitance changes between those conducting plates on either side of it. There's some resistance, so you've got some series loss. And then in parallel with that capacitor in series, you've got a shunt capacitor that's equivalent to the straight capacitance. So you've got basically an RC type circuit. So you see the parallel capacitor, and then the series capacitor, inductor, and resistance, because there is loss in it, just like any other real world device. So that's the actual parallel tuned circuit that it represents. What they call the stiffness of the crystal is equivalent to the inductance, or like a spring, where the capacitance is the mass of it acting like a capacitor. So when you go to the mechanical world of a tuned circuit, like think of a tuning fork, you've got a spring and a mass, and that is equivalent to the inductance and capacitance.
Where does temperature get represented in these? We all know if you take
It's going to affect
if you take a crystal, put it in an oven, it's going to be more stable.
If you control the temperature, yes,
right?
Yes.
But there is no counting for that in your schematics.
Well, you're going to affect the capacitance, both series and parallel. You may affect the inductance of it. If you change the temperature, it's physically going to increase or decrease in size, like most things. It's another reason why you need to keep it from vibrations, because physical vibrations will also affect it.
Well, they have a bunch of crystals in ovens, little oven devices that maintain a very stable environment.
Yeah, that's what I said. Yeah.
That's one of the problems with a lot of radios, that there's drift on the reference oscillator, and you turn it on and you wait a little while until it gets up to its ambient temperature. So which of the following is an aspect of the piezoelectric effect? All right, this is the This is the mouthful one. So what's the equivalent circuit?
Okay,
It's definitely emotional to pass. But
Right.
past that, I don't.
So you can eliminate D then.
shunt capacitor.
Yep, that's one of the keys, the shunt capacitor. Okay, so any questions on inductors? I guess not. Should I do my Lenz's law demo?
Sure.
You understand Lenz's law?
No,
It's about
it's worth seeing.
opposing magnetic fields. Copper, PVC, magnet. So what's going to happen? And I guess these guys, if I unshare, where is my unshare?
We just hit escape.
Okay, can you guys see me? Are you guys Jesse?
All of you.
I can see you.
All right. I'll let you do the honors and catch. Somebody needs to count how long this is going to take. Ready? Go.
One. One, yes, one.
All right, ready? Go.
1, 2, 3. Oh. Cool.
Why?
Air pressure.
No.
Ah,
No. It's a magnetic field, right?
right. But it's copper.
And that piece of copper tube is a coil,
Mm-hmm.
one turn shorted together. So if we take a magnetic field and we run it across a coil,
Well, you get voltage in a magnetic field.
it causes a current to flow.
Yes.
Okay. When the current flows through a coil, what happens? It produces a magnetic field opposite to the magnetic field that's causing the current. So it opposes the magnet.
That was perpendicular.
No, it's opposite. It's like two positives. So it's a magnetic field that's opposing the magnetic field of the magnet. And if you didn't have losses, it would kind of take forever to go down there.
Kind of principle behind like maglev trains,
Uh,
where they're running high current through the rails to.
yeah. And that's kind of how basically a transformer works, because you're increasing the magnetic field. Okay, and due to mutual inductance, that magnetic field is affecting the secondary. And it's also creating a magnetic field, which is opposing it. Okay. So